Okay, so now let's head to one of the most important quantities which we'll need, one of the most important procedures which we're going to need for space applications and in general for communications, and this is the link budget. So we've seen earlier on that, recalling Shannon and recalling what his theorem said, we have seen that power itself is not that important. Okay, so you cannot really compare if a communication is good only by its power. Now we saw in our example that we got very small, very tiny power, picowatts, but that didn't really tell us anything. Okay, so is 1 watt enough? Are 2 watts enough? Are nanowatts enough? We don't know. So the reason why we don't know is because actual communication depends on the ratio of channel to noise, or signal to noise if you like. So the way to picture this briefly is that, okay, so what if you're listening to music which is very low? If you're listening to low level music but you're in a silent room, you can still enjoy it. On the other hand, even if you're listening to very loud music, if there is lots of additional noise, even if the music level is very, very high, you really wouldn't be able to enjoy it. So absolute power is not what is important. The signal to noise ratio is important, always. And we saw earlier on that we have several types of noises and we quantified all of them, so we got an expression for them in terms of an effective temperature, an equivalent temperature which would take all of these noises and recreate their power in terms of thermal noise. So we said that thermal noise was just one of the different types of noises, but even other sources of noise, they can be taken by mathematically substituting their power with an equivalent temperature. So the formula which we're going to use will always be the Nyquist noise formula. So this is always the thing which we're going to be looking at. So the noise spectral density is equal to Boltzmann's constant times the temperature. And this temperature, for our purposes, will be an effective temperature. It will not be the physical temperature of the device. So if our antenna is at room temperature, it may happen that its effective temperature is much higher. It may even be lower, depends. But the main idea is that this temperature which we're going to consider is going to be an effective thing which is not the physical temperature. It's a parameter of the whole system, and it includes into it all of the different noise types. So this is spectral density. This is the energy of the noise per unit bandwidth, and to get the full power of the noise, we have to multiply this by the total bandwidth we have. So Boltzmann's constant, as you may recall, is something very, very small. It's 10 to the power of minus 23, so it's extremely small. So you may think that noises in general are very, very weak, but the thing is that the effective temperature may be large enough and the bandwidth may be large enough that this will actually be quite comparable to our signal. So we computed in our last video, we computed the power we would receive in a communication through the Freese space equation. We had the power of transmitter, the gain of the transmitter, the gain of the receiver times lambda squared divided by 4 pi r squared. And what we should now add in order to turn this into a channel to noise ratio, so this is only the power received, so this is only the channel power, we need to divide by the noise. And how do we divide by the noise? Well, we simply divide by Kb times the system temperature, the effective system temperature, times B, which is the bandwidth of our communication. So we take the power which we had previously, so the power we computed from Freese transmission formula. This is not in dB notation, this is in SI units. And we divide by the total power of the noise, which depends on the bandwidth and the effective system temperature. Now this LA additionally in the denominator is just for any additional losses we may have considered, and it's also straightforward. Now, once we have this, the more important quantity which we're actually after, which you may recall from our previous section on noises, is the energy per bit per unit spectral density of the noise. So EB over N naught, EB over N0 is actually the energy which we have per 1 bit divided by the noise per unit spectral density. So again, the spectral density of the noise. And this quantity we saw previously, which you may recall, that it's directly connected to the error rate of our communication. We're going to see this again very shortly. But first, let's just see how to compute it in terms of regular units. So we take our previous formula, and to get EB instead of E, we divide by the transmission rate, and to get N0 instead of N, we multiply by the bandwidth. And what we get is this. It may look like a very cluttered and ugly formula at this point. So we have the power of the transmitter, the gain of the transmitter, the gain of the receiver times lambda squared, again divided by 4 pi r squared. So this, all of this, and LA, this is simply the power which we had previously, but now it's divided by the rate of transmission, which gives us the power per bit, so the energy per bit. And we also have KB times T system in the denominator, which is the spectral density of the noise. Now this quantity, EB over N0, is actually what qualifies how good our communication is. We're going to see very shortly that this is actually the quantity which we should be after, not the power per se, so not the power itself, but the ratio of channel to noise, once again. Now again, converting in dBs, because we saw that it is much more effective, much easier to work in decibel notation. Converting in dBs, so the EB over N0 is equal to the gain of the transmitter, once again, plus the power of the transmitter, again in dB watts, the gain was in dBi, and this time we have introduced a new quantity, so it's GR over TS. So this is the gain of the receiver divided by the temperature of the system. Now this whole thing is again in dB notation, but we have simply taken these together. So you can see that this is simply the gain of the receiver in dBi minus 10 times logarithm 10 of the temperature. So this new quantity we have introduced is essentially the dB version of the gain divided by temperature. You can think of it as gain per Kelvin. These three terms are everything that adds to our level, if you like. So the gain of the transmitter, the power of the transmitter, and the gain of the receiver per temperature, if you like. And we subtract all of the losses. So we subtract the free space losses, LS, which we know how to compute. We subtract the additional losses, so attenuation, polarization mismatch, anything else you may have. And you can see we also subtract 10 times logarithm 10 of R. Now this term is actually the dB version of the transmission rate in the denominator. So we had R, which is transmission rate, in the denominator of the equation, and when we convert to dBs, we have a minus because it was divided by, and we have this 10 log 10. Now there is one additional term which you may be wondering what it is, this 228.5. This is simply Boltzmann's constant. So this is simply Boltzmann's constant written in dB notation. So Boltzmann's constant is 10 to the power of minus 23. Logarithm 10 of 10 to the power of 23 is just 23, and multiplying by 10 you get roughly 230. So this term is actually just Boltzmann's constant. It is with a minus, but since it's in the denominator it becomes a plus, and so we have this plus 228.5. So this is nothing but just writing Boltzmann's constant in terms of dBs. So this equation, the way you see it now, is actually what we need. This is what tells us how good our communication is. And we can evaluate it if we have all of these terms you see on the right side. And this quantity, EB over N0, is essentially all the information we need about how good our communication is. Of course, we also need to know what type of modulation we have, but this is typically either already chosen or we can just check out for different types. So you see on this graph, what is shown on this plot are essentially the bit error rates, so the rate or the percentage of time in which we have bit errors as a function of this EB over N0. So you see the relation is very similar for all different types of modulation. There are some differences, of course, and this graph tells you how bad or how good your communication is. Okay, so suppose you're using 4QAM. So we saw this, just an example of such a modulation. And okay, you know, you compute, you have the power of your antenna, you have the gains, you have the distance and everything. And suppose that you compute 8 dB over N0. Well, if you look at the graph, this tells you that you're going to have roughly 1 in 1,000 bits which are wrong. So this may be good for you, it depends on the application, it may be terrible, it depends. But if you can do something, if you can increase somehow this quantity EB over N0, So for example, maybe you can get it to be as large as 12. And if you have 12 EB over N0 for this same modulation scheme, okay, you're going to have something like 1 in 10 million wrong bits. So 1 in 10 million, this sounds much better. So out of 10 million bits which you transmit, only one of them will be wrong. This sounds very good now. So this really depends on what exactly you need, on what kind of communication you have, what are the purposes of it. So different values of EB over N0 may be good for something but bad for something else.